So we already learned about the models for dynamic loading. And last time I didn't show you with a PowerPoint, but this time I do have some PowerPoint for you. Okay. So this is one example for how the strength of a material can drop when it's under several number of cycles of dynamic loading. Take steel and aluminum as examples. From here you can see when there's no when it's fresh, it's not under any load, the strength is higher. But as the number of cycles increases, the strength drops. And just like how we talked about last time, the strength will drop to a certain level, and it tends to stay there for most of the metals that we're using. But aluminum is a material that is softer, so it drops with a similar slope, but it drops even more when the cycle time increases. So always check on how the material behaves. And over here, like what we introduced last time, we study the mean value of the dynamic loading, and also we study the amplitude. Okay? So this is from last time. And I'm sorry about the fonts. The equation move around. Okay, this is better. So, this is so-called the yield line, where we believe the worst case of the loading case should be smaller than your upper limit, which is yield strength. So the magnitude plus the mean value of your stress plus the amplitude of your stress would be the worst case, the maximum load you're carrying right here. So if your worst case is not greater than yield strength, you should be fine. The easiest idea is to do this. And if you want to apply safety factor, put it on the right bottom side of your right hand side. Or we would like to rewrite this into this format, because this equation would look much similar to other two models. Okay, so when we apply safety factor, basically we have a more conservative boundary of our design. Our design has to be within this triangle. And the horizontal axis is the average or mean of your stress. For the vertical axis is the amplitude or the range of your dynamic loading. Okay, so for any dynamic loading condition, you need to calculate the mean value and also the amplitude, plug into the plot, find out where your design is. If the design is inside this line, you satisfy this model. For example, if we have a design right here, okay, it satisfies this model, but it doesn't satisfy the safe one. Because for this one, the safety factor, for example, is around maybe 1.5. Okay? So for this design, maybe the safety level is around, here is safety level equals to 1. If this is 1.5. So maybe over here, the safety level is 1.2. So for this design, you only reach a safety level of 1.2. So if you wish to have a design that has a greater safety level, then this one is not good enough because it's not inside the range of this a safety boundary. Okay? Let's move on to the next model, and let me fix this. Okay? And because we know the strength of your material decreases as the cycle time increases. So this is representing the amplitude of your stress, of dynamic stress. So if the number of cycles increases, that will directly reflect to the amplitude, because you are having more fluctuating loads carrying onto the material, and you already separate the mean value and the dynamic one. So for mean value, you can consider more like a static value. And for the amplitude, it's more like a dynamic value, right? And as this increases, as your cycle time increases, the strength drops. That's why in the model of Goodman, he believes that you have to use the limit, the endurance limit as your upper limit for dynamic loading, for the amplitude of your stress. That's why he draws this line from here. And since you are having this dynamic loading, and this is your mean value, the mean value doesn't occur all the time. Okay, it only occurs occasionally. So Goodman believes for mean value, you can give mean value a greater upper limit using the ultimate tensile strength. So at the end, Goodman believes the design boundary could be like that. Okay, so the mathematical equation looks like this. And if you apply a safety factor, you end up with a smaller range of your design. Okay? But when we do this assumption, we allow the mean value of your stress to be as large as your ultimate tensile strength. That's a little dangerous. So for Soderberg, for the Soderberg model, a much more conservative model design was introduced. The most conservative design is Soderberg. So it's a straight line between your endurance limit and the yield strength. And your design space is the smallest. This is your design space. And the mathematical equation looks like this. And again, if you apply a safety factor, your design space becomes even smaller. So this is just a quick review of what we have done last time. Any questions? Okay. If my exam is that easy all the time, I guess no questions. Okay, anyway, let's try to fix this first. And then let's talk about how we can solve a problem when we have shear. This is also a review because we talked about this last time. This is a general case, just like what you see in your exam. And we do have shear. We do have shear stress. How do we put shear stress into the consideration of fatigue? There's no shear stress in the equation. The way to do it is to use von Mises stress. Because von Mises stress is a equivalent stress, which has no direction. It's not a vector, it's a value. And it covers stresses in all directions. Like here, it covers the stresses, principal stresses along x, y, and z, all directions. If you can draw a Mohr circle, if you can calculate the principal stress covers the information about your shear. So for plane stress problems, if you let's review our second exam. This is the radius. If you calculate the radius, this is your height. This is you should use this is a width. So this is sigma A minus sigma B divided by 2. Okay, the radius would be sigma A minus sigma B over 2 squared plus this is called tau A squared. This is your radius, and this is the exact value of your maximum shear. Okay? So from here you can see the maximum shear has information of the two normal stresses that this material is carrying, and also the shear stress this material is carrying. Okay? And if you calculate the principal stress S1, basically it's this value. This value basically is the mean value of these two. So mean value would be sum of them and divided by 2. Okay? Plus the radius. So plus R. R can be calculated here. So this is how you calculate your principal stress, the first one. And once you have S1, you have your first S right here. Similarly, you can calculate your second principal stress. So this equation has the information of your shearing stress. So this covers everything. And this is only single value and can be applied to our fatigue model. Okay, so please understand what we're doing right here. Okay. Is this clear enough? This is the second time we talk about this part. You don't understand? You're okay?
This is like the radius in the
More circle?
yeah, the radius should be.
Did I make a mistake?
I think it's less than.
Okay. Did I do something wrong?
I think you sigma is less than b.
Okay, let's just give true numbers. If this is -2, this is 6. Okay, so over here is 2. So when we are trying to get a 4 equals to 6 minus -2 divided by 2, right? So this is 4. 4 is this guy minus this guy. And when I want to get this position of the center, 2 equals to the mean of it. This is calculating the width. This is calculating the position. So when you calculate the width, of course, you calculate the entire width divided by 2. And this is calculating the mean of it at the center. So you sum them up divided by 2. That's why here is minus, here is plus. Okay? Any other questions? Okay. Since this is already the second time I introduced this, I don't want to waste too much of your time. And we will have 2 videos about this part. So you can always go back and check the videos. And don't worry if you ask any questions, because the easiest way to learn this subject is to ask right away. Okay, the positions of the equations went crazy. Okay, let me correct those. Okay. This is what I'm trying to say. I'm sorry, it's messy. So, if we can apply von Mises stress to our fatigue model, at the upper parts, they are all von Mises stresses, including the average ones and also the amplitude ones. And we can then try to figure out what would be the mean of the von Mises stress and the amplitude of the von Mises stress. So we go back to see the equation for von Mises stress, which is this one, for plane stress or plane strain problems. And also for this particular low case. This value is only for this case, if I'm right. Am I right? No, this is a general case, general equation. So if it's plane stress or plane strain problem, this is the equation, okay? So basically, von Mises stress equals to S1 squared plus S2 squared minus S1 and S2. And if we want to study the mean value of this guy, we basically plug in the mean value of those. That's why we have n right here. So in the problem, you can study the mean of your principal stresses. Just plug in. Then you can analyze the mean of the von Mises. And also for the amplitude, just plug in. This is the easiest way to estimate it. Is it always correct? Let me see if there's a special case when it's not correct. If you have never simulated this, how are you sure? Okay, so what my concern is, when I study a subject like this, my concern would be, is it really, can those be calculated like this? Is it real? Can I just plug in the mean value, and of course that would be the mean of your equivalent stress. What if it doesn't, because when you are talking about mean and amplitude, you're talking about the stress is varying. So what if the way the stress is varying doesn't occur in the way you expect? So I would say this is maybe the best way to describe my doubt to the equation is, let's say you have the first principal stress, this is time, and you have your second principal stress and time. So after comprehensive analysis of your principal stresses, maybe at the end your first principal stress looks like that, and your second one maybe it looks like this. Okay, so at the end this is the mean value, and this would be your average, the amplitude. Okay, and for this case, this is your mean value, and for example, this is your amplitude. Okay, so can we just use those numbers and then determine the equivalent? I think the most accurate way should be truly calculating S1 squared plus S2 squared minus S1 and S2, and of course take the square root. Truly calculate it and calculate in time. And maybe at the end you end up with some fluctuating function like this. This is time. And you truly analyze the true mean and also the true amplitude. When you do that, are you sure this value, the true mean of this vibrating signal, truly is this? I'm not sure, because you did a square root here, and you did minus, and you take a square root. You do square, and this is like a second term as well. You have plus and minus. I'm not sure you can prove this is 100% correct. Is it possible in some particular cases this won't be true? But for mechanical design, I would say this is okay. because we already make a lot of assumptions and also a lot of estimations. I think those are reasonable assumptions. Even though maybe you are a little bit overestimating or underestimating, you still have your safety factor. So safety factor is our safe net. It's like a final trick to increase your reliability. Okay, even you mathematically, when you have some estimation, and you actually have some inaccurate estimate, for mechanical design, actually it's fine. We already consider a lot if this is the equation you are using. Okay, so if you have doubts like what I had all the time, you can truly try it and see if this is always correct. If you truly test it, let me know. Okay, I'm curious as well. Okay, so let's say we are okay with this assumption. We just plug in all the mean values and amplitude values, and we got the mean and the amplitude right here. How can we directly use it? Because this is our original problem. So if the problem tells you, okay, the stresses has its mean and amplitude as well, mean and amplitude, does that probably means you can plug into those equations to estimate the mean of your principal stresses as well. So it's like you have a Mohr circle. So originally, so maybe this is like a moment 1, and you have sigma 1 and tau, okay? And usually you have the other point right here. This is your sigma 2 and negative tau, right? This is how you get Mohr circle, sigma and tau, okay? And now we're saying those values are varying. So if it's varying, okay, why is that? Okay, we're back. Okay, so when we say some value is varying, so for example, this one, sigma 1 is actually a value changing like this. Okay, so you calculate its mean, and you calculate its amplitude. Okay, so it's like this is its mean, and it will be fluctuating left and right because of the amplitude. Okay, so due to the fluctuating behavior of this sigma 1, this point moves left and right in your Mohr circle. Okay, if this point moves left and right, if this is the only fluctuating load, let's say this is the only fluctuating load, the Mohr circle changes. This is the first, and the other guy will be like this. Okay? So because of this stress fluctuates, so the Mohr circle shrinks a little bit and expand a little bit from time to time. So the Mohr circle is like this, changing its size. But this is only fluctuating behavior of one stress. How about the shear and other stresses? Let's say all of them are changing all the time. Then the Mohr circle is dynamically changing its shape. So it will be like a statistical behavior of the Mohr circle So it's like the Mohr circle is going to be changing its shape inside a band. But the shape of this band really depends on how each stress fluctuates. What we can do is we try to get the mean value and the amplitude. So what we're doing here basically is just like we are trying to study. Over here, this is where your first principal stress is. What you are doing here is basically you are studying the mean value and the amplitude based on how the Mohr circle fluctuates. Okay? And similarly, you are studying this guy, mean and amplitude. And again, do you truly get those right numbers correct when you directly plug in the mean and average and the amplitude values? I'm not very sure because you have square roots. It's not linear equation. If you plug in something and it's having a linear relationship, then you are confident what you plug in ends up with the right result. But it's a nonlinear function. So how are you sure if all of your mean values here being combined in this way, you end up with the mean value of this region? How are you sure? So again, those equations are good ways to estimate the mean values. It may not be very accurate, I believe, but it should be reasonably acceptable. So just use it. Okay? Any questions? Okay, so let me clean up some of the notes that I'm using here. So for solving problems, just solve like this. If I give you a low diagram like this, I tell you the mean value and amplitude of the normal stresses and the shear stresses. You can use it to calculate the mean and amplitude of the first principal stress and the ones for second principal stress. With those mean and amplitude values, you can plug into your von Mises equation. You can then get the mean and amplitude of von Mises stress. Then you can plug into your fatigue model. This is where you plug in your fatigue model. The von Mises stress, mean of your von Mises stress, amplitude of your von Mises stress. Okay? So this covers what I talked about last time. Today, now we're moving on to the new concept for today. Today we talk about stress concentration. Why do we worry about something called stress concentration? Because research or experience let us know when the geometry has uneven shapes at some positions, the material tends to break at those positions. For example, if I have a cylinder, okay, think about this. Think about this pen. If I try to bend this pen, you are not sure where it's going to break, because let's assume this is a very uniformly made pen. The material inside is distributed very uniformly. So everywhere of this material, of this pen, is trying to carry the load. But one day, if you make a cut, a small cut, and if I try to bend it again, by our common sense, we are very sure it's going to break like this. How come this tiny notch is going to make this material weaker at the uneven position? The main reason why is stress concentration. Stress tends to concentrate at positions where you have different shapes. So another example is if you have a cylinder and you have a narrower diameter, then stress tends to concentrate at the corners. Okay? So if you bend this material, it tends to break at the corner. That's why we usually do rounding. We usually do rounding at the corner, because we want to spread out the concentrated stress. So at this point, the stress concentrated so much. Concentrated so much. The stress over there could be much greater than the usual stress. Much greater. But if you try to use rounding to spread out the stress distribution, then this is concentrated stress. The stress over here can reduce a little bit. The concentrated stress will reduce. Okay? So this is a very important subject for mechanical design. Before this introduction, we are all talking about models from the textbook, but we rarely talk about situations in real case. This is the real case. In the real world, stress actually concentrates. So as an engineer, how can we still make good designs when we know stress may concentrate? There are researchers already did a lot of experiments to study how much stress could be concentrating in many different geometries, many different low conditions. So they plot out this table, these tables, to give you a guidance about how much stress could be concentrating. Okay, so I will let you know how to use it and you need to understand why this table is happening and what does it mean. Okay? So, before we move on to the table, we need to understand the definition. There is something called stress concentration factor, K. We will be having several different Ks, but in general we use K. So what would be the easiest way to understand K? K basically is the highest stress over the reference stress. So take this one as an example. If we have a cylinder with two different regions with different diameters, can someone tell me, here is A, here is B, if I do bending, which part carries greater stress, A or B? Should be very easy. Right? I have a cylinder like this, two different parts, different diameter, same bending moment, but which one carries greater stress? B, yes. Then can someone tell me why?
Smaller area.
Yes. Basically, a smaller area to carry stress. When you have smaller area to carry stress, the area tend to have greater stress, greater pressure. So, when we have a component like this, we don't care about A. We don't care. Why? Because A doesn't carry greater stress, B carries greater stress. So usually what we will do is we consider the stress in the B region as our reference stress. Okay? So in this case, this is where this workpiece is carrying the most stress. But besides the stresses inside the region B, there are some positions that could be having even greater stresses because due to the effect of stress concentration. This is those corners. So can you tell me how much concentrated stress that will be? The way this research is done is to tell you how much stress this corner will be by telling you this. K times the reference stress. So the table is telling you how many times of your stress and how many times of your reference stress that you will get at the corner where the stress concentrates. Okay, so when you get a value K, K means how many times? Okay, because this is your highest stress, basically where the stress concentrated stress, and this is your reference. So the concentrated stress equals to K times your reference stress. Okay, so this is an important idea. So let's try to read the table. Now, the drawing is not very clear, so let me highlight some of the features, some of the symbols. Those values right here are capital D over smaller d, and here is basically R over small d, and here is KT, and this is stress, this is diameter capital D, diameter small d, radius of the rounding. Okay? So from this table is telling you if I have smaller value of R over D, if I have smaller value of R over D, then let's take a look what's gonna happen. In that case, we focus on one particular case. let's say our d, capital D over small d is constant. So in this case, when we have smaller value of r over small d, we will have increasing value of k. Increasing value of k. So k increases. And let's start to try to understand why. When we have smaller value of this, r over d, that means we have smaller sizes of your rounding. If your rounding is too small, if it's too small, k increases. If you have zero rounding, your k could be as large as infinity based on the trend, or very large. So when you, one day if you are making a workpiece by the tool machine, always have some rounding at the corner. Otherwise, your workpiece will be so weak because that corner carries so much more times of your reference stress. Okay? If you can, let's say we wish to have similar stress, so you wish your k is close to 1, then it's almost impossible, but for the lowest case, right here, this one is telling you, okay, I could have as low as 1.2 sigma reference, 1.2 times my sigma reference. So in that case, I probably need to have a ratio of this, something right here, 0.2. So your radius needs to be as large as 20% of your diameter. So it's like when you're designing this is your small d, you need to make a rounding that is having a radius of 0.2 d. Now you kind of have a sense how the rounding should be in order to have a lower level of your concentrated stress. Okay? So let's take a look at the second factor, which is capital D and small d. Right here, this very top curve is having a value of 2. And the very bottom one, this is 1.01. Okay, the two extreme cases. If you have greater ratio of capital D over small d, your k increases. If you have lower ratio, which means the difference between the thicker one and the smaller one is not significant, only slight diameter change, then your stress concentration won't be a big issue. However, if you have like this pen is having a thicker body and a thinner cap, so there will be stress concentration in the corner. Okay? And when the ratio is up to 2, which means if you have a design like this, if you make an engineering drawing like this, this is your capital D, and if you have half of your capital D right here, and let's say you pick a rounding of R equals to, let's say 10% of this guy. I think it's a quite common design a student could be making, or any engineer could be making, where you have a thicker part having a capital D as diameter, and you have a thinner part right next to this thicker part. and the diameter is half. And the person has some sense to prepare some rounding, which is having 10% of the smaller region. And let's see what's going to happen. So the ratio is 2, so that would be this curve. And R over small d is 10%, so it's right here. So this point, 2.0. So for this design, the stress right here, concentrated 1, equals to 2 times of your reference stress. So this is where you get your reference stress. So before this class, you may not understand, for a design like this, the concentrated stress could be as large as 2 times of the stress that you usually get. Okay, so this table is actually very useful. And the trend varies when it's carrying different kinds of loads. This is pure tensile, this is bending, and this is twisting. And from here you can see the trend varies from case to case. So you need to understand what kind of loading this material is carrying, and you need to know which table to check. Okay? Is this clear? Okay? So for tensile and bending, this is basically pure tensile stress, and this is bending. They all apply normal stresses to the. They both apply normal stresses to the workpiece. But for this one, this is twisting. Twisting will lead to shear stress to the material. Okay? So the difference between these two cases and the third case are how the stress is being applied. Directional wise, they are applying the stress in different directions. So usually when we have normal stresses, we use the symbol of KT, okay? And for the shear cases, we use the symbol of KTS. So S is representing shear, okay? T is representing something else. I will let you know. T is representing static load. Static load. Okay, so these two tables are the stress concentration factors for static loads and also normal stresses. This one is a stress concentration factor for static load and shear stress. Okay, so please make sure you understand this. So static and normal. Over here, static and shear. Okay? So in the future, if you are carrying static load and normal stress, then basically it's pure tensile or pure bending. Then you need to decide which table to use. For the third case, if it's twisting, then you have shear stress. But those are for static loads. Okay, so I would like to write down a table so you could easily memorize those. KT and KTS. So here is normal stress and shear stress. And now we are talking about static loading. Okay, we have two more. We have two more. Okay, everybody okay? This is the subject that you didn't learn in the past. Only this course will tell you about this knowledge. So it's usual if you have no idea what's going on. But I wish you can understand what I'm trying to introduce. So let me move on. So how about the dynamic loading? The way researchers approach this this area is they figure out the stress concentration behavior varies depending on the size of the notch. Okay, so there is something we call the notch radius. So what's notch radius? For example, if you have a geometry like what we have drawn, you can consider this part as a notch, and you can say this is a notch radius. Basically, the location where you have geometrical change and then the radius of it. Another case would be like this. If you have a notch like this, and since it's not rounded, maybe you can use this distance as your radius. Or if you truly have a shape like this, then definitely the radius of that circular notch, that rounded notch, could be used in this table. So basically, it's trying to study the size of the notch. Okay. So let's try to understand this quickly by analyzing the tables. So over here, basically, is your R. If you are talking about this case, the cylinder again. This is capital D. This is small d. Okay. Okay. The cylinder, and you have your rounding right here. So if that's the case, over here, there's a value called notch sensitive, and we use the symbol of Q. Okay, so this is indicating how sensitive is your stress concentration based on the size of your notch. Okay, so in an extreme case, let's say this Q equals to 1. What does Q equals to 1 mean? When Q equals to 1, that means this equals to 1. So I will have something called Kf that will equals to Kt. So what is F? F is going to represent dynamic loading. Okay? So in fact, here is Kf. And this is about dynamic loading. Okay? If we have a Kf, we also have Kfs. So dynamic loading and shear stress. So let's get back to the extreme case that we talked about. If there's a material that has a notch sensitivity of 1, that means Kf equals to Kt. So Kt was from the previous page. So if in one case, like what we show here, we said when R equals to 10%, R over D is 10%, and we said D over D is 2. This is what we had earlier, and we are using, we are pulling it. We're pulling it. So we found KT was 2. We found KT was 2. So if this material is having Q equals to 1, that means KF is also 2. Okay? So that means when this is large, that means this material is also sensitive to the geometry of the notch. Okay, but how about another extreme case where we have a lower sensitivity? So let's say if there's a material that only has Q equals to 0.5. If that's the case, if I change the material and I say K equals to 0.5, in that case, you will see Kf minus 1 equals to 0.5 times Kt minus 1. And T is, Kt in this case is 2. So at the end, this is 0.5. And at the end, Kf equals to 1.5. It is lower than the first case. So let me sum things up. For this case, d over small d equals to 2, r over small d is 0.1, and in this case, also if I choose a material has Q equals to 1, it ends up with Kf equals to Kt, and they are both 2. And if I have another case, Q equals to 0.5, at the end, Kt was still 2, the Kf drops a little bit, 1.5. So, which one is better? If I want the material to be safer, which one is better? Lower the better, right? Because lower stress concentration, lower stress, safer design. So of course we wish Q is lower, so we can apply dynamic load to it. Okay? So if we want a material that carries lower K when you are applying dynamic load, then let's see what's happening. Lower K. So if you have smaller notch, actually, hold on, am I right? Right? Does that make sense? KT is 1.5. Yes, that was right. Smaller notch, you may have smaller Q. Yeah, sure. Because if there's no notch, then if there's zero notch, so for example, if I have a cylinder like this, if this is so small and the radius becomes 0, then Q goes to 0. If Q goes to 0, then your Kf goes to 1. Because 0 equals to Kf minus 1, Kt minus 1. So Kf equals to 1. If Kf equals to 1, that means this is so small and the stress over here is the same as your reference stress. This means stress equals to 1 times of your reference stress. Okay, so smaller notch actually gives lower Q. Lower Q gives lower Kf. But the trade-off is when you have smaller notch, for static case, we may have smaller KT. We may have larger KT. So you cannot have, this cannot be too small. If you have geometry that that could break easily, okay? So let's get back to this table and see what also varies Q. Here is SU, ultimate tensile strength. So this table is telling you for harder materials, it's having greater Q. Softer materials has lower Q. So it's like a harder material can survive fatigue. I mean, softer ones can survive fatigue. I think that kind of makes sense. If you are strong, you are hard, but you fatigue more easily. But if you are soft, you're flexible, you are able to sustain longer dynamic loading. Kind of have that kind of view. Okay, so this is the table for Q here. And here is the table for QS. And they are sharing very similar equations. So over here, Q equals to KF minus 1, KT minus 1. QS equals to KFS minus 1, KTS minus 1. Okay? So the procedure is, when you are concerning about stress analysis, stress concentration, you can check the first several tables here to study what kind of loading case you're having, what are the geometrical parameters you're having. Then you can estimate what is your K. So you will either have KT or KTS. Depends on whether you are having normal stress or shear stress. Once you have KT and KTS, if you are also carrying dynamic loads, you want to worry about the fatigue, then you need to check these two tables to study Q, the notch sensitivity. Once you have KT and Q, you can estimate KF, this guy, the stress concentration factor for normal stress in dynamic loading case. For shearing case, you need to first have KTS, use this table to get QS, then you can calculate KFS. KFS will be the stress concentration factor for the shear stress in dynamic loading case. Okay? So that's basically how this is how to consider stress concentration. Okay, so how would those equations, I actually have this here. How does these equations help us when we try to solve a problem? This is basically what I said earlier. Okay? How do we use it? So let's get back to static loading problem with stress concentration. So in static loading, we had 3 different kinds of models, just like your exam 2. Okay? So in your exam 2, we never talk about stress concentration. Now, if stress concentration is an issue, then you need to figure out how to apply those factors. For Mohr circle, so let's say I have a geometry like this. This is usually for a shaft, right? So this is, if I have a shaft design, okay, and so maybe I'm analyzing, if you study where this shaft is carrying the most stress, basically the corners. Okay, so the corner, and if we happens to have bending and twisting at the same time, so moment and torque, then those corners are carrying both tensile stress and shearing stress. Okay? And we cannot just analyze the way we did it earlier, because we know stress concentrates. So without stress concentration, we know this is 16T over pi d cubed, and this is 30 M over pi d cubed. But in fact, we need to apply stress concentration factor. And over here, you can multiply a K. Here's another K. For normal stress, from previous introduction, I should have KT. And here is shear stress, I should use KF. Okay, KS, sorry. KS. So what's gonna happen is, when you study your Mohr circle, when you work on your Mohr circle analysis, all the values right here becomes greater due to stress concentration. And they are K times larger than your reference stresses. Basically, these. Okay? That's simple, just applying a new number. But how do we get KT and KTS? For KT, so basically you need to get back to that D over D, R over D, KT table, and you need to find the case where you have pure bending. So you need to figure out the dimension, and then you need to then figure out, okay, how much KT this workpiece is gonna have. And for the other case, KTS, you need to check the table where we have twisting. Okay? KTS can be determined by the table with bending. KTS could be determined by the table with twisting. Okay, this is how you, not KTS, yes, KTS. KTS. Okay? So, let me remind you which two tables. Here. This is bending, and this is twisting. Okay? So you need to plug in numbers and then figure out what's the K. Here, plug in numbers, what's KTS. Okay? And that's how you can get how much greater stresses you will have, you will be having. And for the rest, the same. Okay, just plug in. How about fatigue? So for fatigue problems, those are our fatigue models. And we said we apply von Mises stresses. Those are the von Mises stress equations. But now we are dealing with possibilities of greater stresses, like this one. Okay? And because we separate the dynamic loading condition into two, we consider the mean value part of the dynamic loading as a static load, because it's just a mean value. And we consider the amplitude part as a dynamic load because of the amplitude. So when we try to calculate the stress concentration factor, we use different case. So take this one as an example. This is the mean of your first principal stress, S1, right? Since it's having mean, so you have mean stress here, mean tau, but because they are mean values, so we will treat them like static loads. The K factors are the static ones, KT and KTS. Okay? How about the amplitude? When you are dealing with amplitude of your principal stress, they are varying stresses. So those stresses are values that changes all the time. And that's why when we apply stress concentration factor, we will be applying the dynamic ones. So over here, these two are normal stresses. So we apply Kf. This is shear. And this is dynamic case. So we apply KFS. KFS here. Okay, so I think this table will be very useful for you. And when you try to apply K's, you will know which one to apply. Never try to memorize all these. It's impossible to memorize them. Yeah. That's why I have been talking about this for multiple times, because I know it is going to be very messy later on. If you put these into these, and put this into this, imagine how long the equation is going to be. Very, very long equation. This is the extreme equation, the longest equation at the end. Did I already apply? No, I didn't. I didn't try to plug in. Maybe I show it once to you. So let's try to plug in and see how the equation is going to look like if you try to memorize it. In the past, when I taught this course, I saw students truly try to memorize the whole thing. I cannot believe how is it possible to memorize the whole equation. So if you try to plug in, so let's say we use a Soderberg model. So at the end, what you will have is actually So this is how it looks like when you plug in the von Mises stress. And then what you need to do next is going to be like this. So it's so long, it's almost impossible to write it down. So let's just plug in some of them. Let's just plug in this guy. Okay, so this is going to be KT sigma mean over 2 plus KT sigma mean over 2 squared plus KTS tau mean squared. And the square of this whole thing. Too long. This is only this guy here. Right? And what could be even messier is that when you apply this, 32 if you apply the 32n over pi d cubed to your sigma, it's even messier. And the square of this whole thing. So if you try to analyze deeper, this can be replaced by this, right? So if you try to derive the extremely long equation of this, you can, but don't memorize it. Okay? I remember when in the past, I tried to write it down in the entire whiteboard. It took me the entire board to write it down. I don't think we need to. Okay? So that would be the end of the day.